Yeah, okay. So we've talked about basic bits. Now we go and talk about advanced bits. We'll briefly go into JCStress advanced topics. And JCStress advanced topics mostly deals with what problems would you encounter if you decide to re-implement JCStress from scratch. Or this is like the shameless discussion about what have we spent 10 years going back and forth in JCStress. The empirical testing is basically dealing with this bad triangle of problems there. If you do empirical testing like this, the probabilistic case, you want to have lots of coverage because you want to cover lots of cases. You also want to run them fast, and you also want to have a lot of interesting samples in that thing. And your implementation choices in your harness basically kind of go against these trade-offs. For example, you can, if you want to cover like 10 more cases, that means your runtime is 10 times as much. And if you're already running for a day, now you're running for a week, making that impractical. If you want to collide collide threads more often, that probably means more synchronizations, which means your fidelity probably goes up, but your speed, testing speed, the number of samples that you get from there goes down. So you always kind of balance in this thing. And in this section, we'll briefly cover what a good harness like JCStress would do to improve on this three things. First of all, JCStress architecture is like this. It runs, if you're familiar with how JMH runs, it runs pretty much the same. There you have a main JVM which runs for the entire run. It does not run any test code at all. It's mostly the orchestrator, if you will. It does capability testing, it schedules stuff, it manages VMs, handles errors, handles result processing. For every test, we are forking the VM. We are starting a new VM, not for the last reason, because we don't want to mix up the profiles, for instance, between the tests, because that obscures some of the things there, but also because we want to run in different JVM configurations. And one of the few ways you can do that if you start JVM with a specific set of JVM flags, which means you have to start the JVM, right? In there, you have task loops, which run kind of the infrastructure code. Each thread gets its own task loop. They are synchronizing with the special utility class, which is called here workersync. They're basically rendezvousing in the particular points. We will talk about that later. And they also, every of this loop enters so-called run loop, which is the smaller, much hotter loop, which calls the actors themselves. When you do this kind of thing, you kind of have the normal, and since you are the harness that basically generated the code that runs these test loops, you can actually say which methods are inlined or not. So you can force inlining, for instance, of actor methods to the run loops, and forbid inlining of the run loop into the task loop. We will talk about that a bit later. But this is kind of the architecture. The good thing about architecture is that, except for the actor code itself, harness basically has the freedom to control everything else. Most of the scaffolding is generated at build time, which is good. So what do we do in harness like this? If you want to increase test fidelity, we generate most of the stuff at the build time and assume the role of the optimizing compiler where possible, because some of the configurations that we will be running are probably running in the interpreter mode, where optimizing compiler is not available. So you cannot really rely on that your infrastructure would be aggressively compiled so that it runs fast. We initialize most of the stuff in the host VM. If you need to do any of this sort of heavy lifting, unpacking dependencies, etc., you do this in the host VM, not in the forked VM. And you only do absolute minimum in the forked VM. Basically, when forked VM starts, you already know what test you're running and what configuration you're running, where to put the results, how to configure the VM is already pre-configured, etc. And for the coverage, since we have the ability to fork VMs, we can run it in the interesting mode and interesting affinities there. We'll talk about this in this section. But first, the stupid problem. And the stupid problem is this. If you run JCStress and you want to improve speed, you want to run multiple VMs at once, which means you are running like tens or hundreds of VMs on your machine, which means you have to at least trim the heap size, because otherwise your tests will out of memory there. So you have to kind of guess what is the good size there. JCStress does, for example, if we go here, API basic JVM01, in the initialization, it will say trimming down VM heap size to some particular thing, because it knows that it will start like 60 other JVMs, and we want to have the leeway for the host machine to do stuff. But this is like this simple issue. But then once you trim the size, you also realize that users can come in and do the tests which have lots of data in it. For example, you have a state test which has the array of a megabyte of byte array in every state. And since your infrastructure is basically allocating the array of the states so that threads can rendezvous on those states, that means your footprint can be unbounded, basically. So to cater for that, you basically have in your generated code, have to go and do stuff like sanity check footprints, where you basically do the runtime experiment right there in the VM, in the particular configuration. How much heap does it take to run the test? How much heap allocated by the actor methods, by the results, etc. And so you can trim the stride size that you use, knowing that you cannot blow the heap size that you have limited. Yeah, it's kind of the boring problem that has to be dealt anyway if you want to have generic testing frameworks. The same thing with the thread counts. If you run the single JVM, if you run a JVM on your host machine, it would think that the machine is exclusive for that JVM use, which means if you run it on my Threadripper, it will just start 64 threads for GC, 64-ish threads for GC, for compilers, for whatever is there. And that will also make the whole run problematic, because you will trash the system with threads while you still want to run. So JCStress does like this, things like this, right? It knows Hotspot very intimately, and it knows what to say to Hotspot to actually trim down all the madness that is available, that is there in the Hotspot VM. Right? It's surprisingly problematic and surprisingly improves speed and fidelity if you do this kind of thing. Again, boring, but very effective thing to do. Coverage. Some tests might only fail with some compilers, or maybe without the compilers, which means if you want to run the concurrency test, you want to run it in the different compilation modes. If you run the modern Hotspot VM, there are at least 3 ways your code is executed. It may be executed in the interpreter, it may be executed in the baseline compiler, which is usually called C1, or in the optimized compiler, which is usually called C2. In the tiered compilation, there are intermediate level of compilations that your code goes through. But for kind of production-like testing, you really want to have at least 3 of these configurations at any time. So if you run JCStress in the particular mode, I would just eliminate, turn off some of the features that I will talk later. It will say that, hey, look, I would go to your JVM and I would ask, what can I configure it with? And these are the configurations the tests will run. interpreter, compiler, etc. It's kind of dubious to ask user to know about this stuff. It's the hardest job to actually run all these interesting configurations there. All right. And some outcomes only manifest in odd compilation conditions. For example, if you have the barrier schemes around volatile variables, since you have two different compilers in your VM, you have two different backends, and you have two different worldviews from these compilers how to emit barriers. So if those barrier schemes are different, and that construes a concurrency bug, you want to catch it somehow. So there are cases when you compile actor 1 with C1 and compile actor 2 with C2, and you have problems meaning the outcomes that you should not see. But how do you configure that? There is actually a very nice thing. It's called compile directives. Compiler control job, which basically says, hey, look, since Java 9, I can go and define a file in which I can go and ask that for the particular configuration for the particular methods. And since I'm the harness that generated all of the scaffolding code for our tests, we know exactly what methods we run. So we can configure them more or less exactly. So if you look at the current way JCStress runs it, you will see something like this. You will see, look, here's the example, basic JVM data races, and it runs with a split compilation where the writer thread is interpreted and the reader thread is compiled with C2. And there are all these juxtapositions of configurations that is there tested at the same time, because you don't know where the trouble is. You want to cover all of these, looking for these troubles. Greatly increases fidelity. All right. And also, since many problems are compiler-induced, you want to instruct the compilers to randomize some of their choices, because you can be lucky for compiler to always have a single lucky choice, even though, say, some reordering is technically allowed, but compiler always make the choice that obscures some outcome. You want to randomize that. For JCStress, there were at least two options that randomize basically instruction selection in the C2 compiler. Other options were added later. So if you look at the options here that I showed you before, yeah, it also tests, JCStress also tests, well, here basically, what diagnostic options are available in the target VM. If those are available, it will just get the configuration that enables those options, looking for trouble again. Many things reproduce with these fuzzers, not with the your usual default configuration. This kind of tells you what compiler could do with your minor example there. Right? This partially answers the question that I had in the first hour. If it's so hard to do, if it's so hard to show in smaller samples, does it worth worrying about? And I answered that it is, because in the larger thing, I can do, my compilers can do actually weird stuff. And here I kind of force compiler to show me what it's got, what it can do with this code by fuzzing it. So kind of boorish stuff. JVMs very like short and negative loops. They optimize it really well. So I already told you that this run loop with the actor is very hot. Since we are already doing these compiler directives flags for split compilation, we can also right there say that we forcing the inlining of this actor methods into the run loop and make sure that run loop is not inlined into the task loop. So VM has really, or the compiler that works on our code has really the most opportunities to actually do stuff with our code without having anything else in the way, right? And fidelity, again. When you do this kind of rendezvousing between the threads, these tests are rarely symmetric. Tests are rarely run at the same pace, which means if you just start the threads and wait for them to run until the end, they will probably outpace each other. So what you really want to checkpoint them every so often to say, okay, now we wait for everyone to catch up and start again, hoping that we will encounter the race at this point, even if those threads are asymmetrically running. And do that numerous times. We kind of increase the probability that we will have collisions between threads, which will give us interesting results. Yeah, here we have the collision windows, which are basically between these checkpoints. Yeah. The choice of how long to run between the checkpoints is interesting, and it's usually like educated guess. But if you don't do this kind of checkpointing, you will lose lots of cases. All right. And finally, many cases that are hardware-induced are manifesting only when actors are running on specific topology. Meaning, some of the cases reproduce if the threads are running on the adjacent hyperthreads within the same core, like we have on this picture here, the red bar in the left bottom there. Or we can have the interesting result only when they are sharing the package, but running on the adjacent cores. Or we can have the interesting results when the threads are running on the distinct packages. You cannot really ask for a lock here and just start the threads and make sure that, and ask operation system scheduler basically to schedule them in the lucky orders, right? You have to make sure that you cover every one of these cases. Of course, if you just kind of do this Cartesian products of all CPU IDs for every test, it would quickly explode stuff. But you can do smarter things like, for example, here, it says, look, we can poll the topology. For instance, this is my Threadripper. It has 32 cores per package, 2 threads per core. We know the CPU lists because a Linux file system basically tells us all of this. And we say that on this system, it makes sense to run the test in the following configurations. We can run it with on the same package and on the same group. This is package group and core group. Or we can run it on the adjacent cores in the same package. The package group is the same, the core group is the same. And we will see this in outputs like this. I'll see, hey, look, this is the data races test. Scheduling class is like this. Please allocate distinct cores, and we will indeed see that they are allocated on the different cores. I have the example that shows why would you do that, but we can probably move it to the discussion zone because there are JVM cases to cover. But it's kind of self-obvious that you want to cover many of these topologies that if you want to do high fidelity testing. Then in that checkpointing thing, you have to wait for the threads. If you do any sort of synchronization, you probably tank your fidelity and speed. So you do busy loops, but in that busy loops, you can make them in different styles, and the choice of that style also matters. In JCStress, it's selectable. There are basically 6 ways to. Where's worker sync here? Yeah, There are basically the hard spin style when it's just spinning on the volatile variable. There's thread yield, which basically says spin, but also yield, or do thread spin waiting. By the way, it tells me that it's not available here because it's only from Java 9 or log support part nanos. And the thing is, it's kind of a weird choice which underlines this trade-off between speed and fidelity. Notice here that if I go from hard to thread spin wait to thread yield, the number of samples grows, the total number of sample grows, right? Because it becomes faster generally. Because if I'm hard spinning on, say, adjacent hyperthread, I'm stealing the resources from the other hyperthread, and that thread could not progress yet. Thread spin wait kind of helps that a little bit. But as speed grows in that direction, notice the frequency of the interesting test case, which is 0, 0 there. It goes down because you have the synchronization that stalls threads for more, which means you are missing the opportunities in your collision windows that you would not that you would like otherwise to have. Some cases like log support parknanas, which basically blocking thing, tanks both of these criteria. Yeah, it's neither fast nor high fidelity. Yeah, so and also thread spin wait is not available on Java 8. So your harness again has to decide which one to use in the particular case. All right. And another thing about fidelity, we kind of glanced over this before, but suppose your concurrency test has two fields. Those fields are probably adjacent to each other in memory. And if two threads are working with these fields on their own, it probably means that those fields are false shared, even if threads are not really sharing each of those. And this hides a lot and lots of behaviors. So if you do something in your harness that makes sure those things are not false shared, you can win a lot. JCStress, for the tests that are in the JCStress tree, auto-injects contended annotations on these fields. So those fields are kind of distinct in the memory, but that explodes the state size there. So, right. Another interesting problem for the API and the tests are written in such a way that both results and states are single use, which means that you want to reallocate them, right, on every stride, but you are running through them very, very fast. So your allocation rate is very, very bad. So if you have the opportunity to reuse these instances, for instance, by cleverly clearing their fields by the infrastructure itself, you win a lot. So without reuse, the dump test runs about 20 times slower, right, than with reuse. Yeah, if you are hunting the very rare samples, you want that kind of speed up because that kind of improves your fidelity a lot. All right. And the dumb things like Java semantics, if you have the actor which has the result and you put things to R1 and R2 there, the Java rule says that, well, look, we need to null check R before we do this. And null pointer exception can only go from the first statement. And we should not really execute the second statement until that condition is checked. So this kind of thing, if done inaccurately, again, hinders the opportunities for the tests. In JCStress, there are special things to actually pre-check R for nullity in the method that is guaranteed to be in the same compilation unit in which actor is in line, so that data flow can actually go and see that this thing is not null. Definitely, and do not do the null check here. Also, very intricate stuff in JCStress there. I kind of glanced over it, but actually, if you want to read how it's done, you can go and say, look, this is the basic, say, basic JVM data races test, right, that we've seen before. And there is the auto-generated file for it, which is generated by JCStress. And here you can see all of this. You can see footprints checking. You can clearly see task loops, which spin here with the worker sync, providing the synchronization, providing the checkpointing, etc. You can clearly see run loops. You can clearly see how it's done there. Yeah. This is, for example, how do you avoid null pointer check on the result in the hotspot speak. You go and access the synthetic field from that result and sync it here into the empty method. And that is enough to cater for the Java semantics for the null pointer check, because NPE would be checked here. And by the time you actually call into the reader, the R is guaranteed to be not null. So, things like this, which are kind of boring in themselves, but when they snowball and compound, you have more fidelity in your testing. All right, we can stop for questions, I think, and then we'll go for the advanced JVM.
Yep. Yeah, we have a few questions. Yeah, let me start with the most interesting one from my point of view. Is it worth to using stress like LSM that randomize the compiler stuff? Options for CI test on the regular, for example, simple Spring Boot application on the CI.
Yes, I think it would. But the problem is, suppose you have a failure. What do you do then?
Well, you explore.
Yeah, you explore, but at that point,
ideally.
Yeah, but at that point, you have to be a compiler engineer to actually understand what's going on. These flags are really useful when you have reproducers ready. In JCStress, like example, you basically have a reproducer ready. If something fails, you just dump it, and that's it. If you have the very large application that you, or the application that you cannot actually give to the compiler engineers, then yeah, you can run, but what would you do when it fails? So
yeah, that's a good point. Okay, and from Andrei, how much work went into JCStress support in the JVM itself, e.g., force in line and other compile fine-tuning stuff? Oh yeah, and that I'm sorry that my question was slightly similar for that flags. To randomize compiler stuff, we have to support it, but when you go to C2 codes, it's like wow, it's huge, it's hard, and so it seems like we make the life for C2 even harder.
Yeah. All right. Not much was actually done in JVM itself, apart from this instruction fuzzing thing, mostly because JVM already provides lots of these things. Well, Hotspot provides lots of these things for compiler engineers. You only have to know what to do with them. For example, that compiler control thing is not JCStress specific. It's just something that is available as the capability in Hotspot VM. And to answer your question, fuzzers are not actually that hard. You have to find like a single if statement where you do the cost estimate for the instruction scheduling and just randomize that. That's about it. It's not that hard. It's hard to find where to put it, but it's not hard to explain why it's there and how it works, etc.
Okay, gotcha. And yeah, the question about GraalVM, what changes in the usage of JCStress if I use a GraalVM instead of a regular JVM hotspot OpenJDK?
I think JCStress would, not auto-detect most of the stuff that's available in Hotspot, and you will run in the limited configuration, which might still be interesting, but so you will lose probably split compilation because there are probably no compiler directives there. Yeah, you'll probably lose inlining, etc. But otherwise, I think many of the techniques that are used in JCStress are pretty generic as far as digit compilers are concerned. So yeah, do try. I know that Graal people run JCStress. It's not the first class support for, there's no first class support for Graal VM. It's mostly hotspot centric. But yeah, I know it runs, and I hope it finds actionable issues in other non-hotspot VMs.
Got it. So it should work out of the box, right? Without any.
Yeah, with caveats. Yes, you want the most fidelity, run hotspot.
Okay, gotcha. And yeah, probably the last one from me. So when you block something with Park Nanos, so usually because of the system scheduler, it might be much. The pause might be much bigger than you
Yes.
wanted to just park on the 1 nanos, but it might be a millisecond or within a second. Yeah, and you make. So when you schedule a lot of the JVMs, you may affect. You will make this effect even more.
Yes,
right?
But do remember that tests are affinitized.
So the thread affinity should solve this problem.
So the hardness, so the host VM, when it schedules stuff, it actually maintains the map of the active CPUs. So when it knows that it wants to run the test which needs these 2 cores, it would only run it when those cores are available, and it will record that these cores are available. And it will basically task set them and then internally do the scheduling affinity calls to bind the actors there. So yeah, it's less problematic than you think, but the blocking nature of this call means that you spend way too much latency there.
Okay. Yeah. Now I see. Yeah, so if we do task set, that makes sense. Yeah, and so but you said task set. So it seems like it doesn't work on Windows, or so I mean it's Linux only.
Yes. If you run on Mac OS or Windows, task set is probably not available. Well, it's not available on Windows. It's probably available on Mac OS if you brew it. It's like TBD work. Some of the affinity work is basically JNA kind of OS specific calls, which are technically possible in every OS. You just have to write them and contribute them to JCStress. Our major target is Linux, because Linux is so nice with the APIs. You can try to get the topology out of the Mac OS, CPU topology. This is a nice exercise in frustration.
Really?
Yeah.
So there is no such nice run proc.
Yeah, you can probably know how many sockets and cores you run, but good luck mapping them to the CPU IDs. Or maybe I'm just stupid and I have not found the way yet. But yeah, prove me wrong by submitting a PR.
Yeah, so PR welcome. Okay, and the last probably funny question: are there any modern and popular JVM that did not pass of the JCStress test? And if no, should we be worried?
Not that I'm aware of. There are plenty of bugs discovered by JCStress, but all of those are fixed.
All right, great. So I think we can move on. Thanks for your answers.
Yeah, okay. So we will be talking about the advanced samples now. They are in the folder advanced there. And there would not be any slides here. I will only go there simply. So let me go to here. So Ivan, a question to you. Suppose you have these 2 variables, x and y, fields, and you have the thread which says synchronize this, x1, synchronize this, y1, and you want to ask the casual observer what are the values of x and y. And I would even read them as volatiles to make ordering questions out of the question.
Oh, yeah, that's a tricky one. But I know that we can kind of squash to synchronize block one to another one. So we can consider this like a single synchronize with this and x equal 1 and equal 1. So I would say it is possible to see something like I would say it is possible to see at least a rewarding. So it might be one of course, but 1 and
yeah. Let me ask you a more specific question. Can you see this?
Yeah, that's so y is 1 and x is 0. Yeah, that means I think yes, because so we just squashed the synchronize, we rewarded them, and now we have it.
Yeah, right. So notice that the observer is not synchronizing on anything. So it's the outside observer, right?
Yeah, and
if I had the synchronized this around these two statements, then this result would be forbidden, obviously, right? Because I would have to wait until either this one or this synchronized block had finished, or that the call-less block has finished, right? So I would not see this. So it goes against kind of your intuition that synchronized, when you exit the synchronized, that this brace here means something. Meaning, I don't know, flushing caches, publishing X, etc. JVM actually allows observing this, and let me try and run it. There's the one-liner here. Oh, I had to restart it. Sorry. Yes. And you're right. One of the reasons why it's possible that you can coalesce the section there. Sorry. What? Okay. Sorry, my JDK is set up wrong. Let's do it here instead. Okay. Which test is it? Advanced JVM synchronized barriers, right? Let's wait a little bit. And you already can see the result like this, right? 0, 1. Yeah, and it happens exactly as you said. Hotspot basically coalesces these two synchronized statements, and then it's set up for the ordering of X and Y, which is allowed because no synchronized observer could see this, right? So synchronized action, if you don't observe it, means nothing. That's the takeaway from this example.
Yeah, is it possible that JIT actually just removed that synchronized block because it see that well nobody cares except
there would be example. There would be example like this. Yeah.
Okay.
A bit later. Yeah. Oh, actually, well, why don't we just do that? I mean, it usually follows the narrative of samples, but we can do as well. Example like this. Same thing. X and Y. X again. Assignments, and between them is synchronized on new objects. So the thing is, can you see this outcome? 0, 1. So can you see 1 here and then here?
Well, yeah, because we discussed it previously. Yeah, I think yes. Yeah, so we can just throw away and
let's just run it and see if it reproduces. It's synchronized. Oh, sorry, it's the Java home is all wrong. I'm running the latest thing, so I opt in all this affinity and split compilation stuff. And there is, right? So we want to run it, and we want to do this thing as a fence, right? but it's not a fence. It's something that's completely eliminatable. If we do actual fence, if we go to unsafe and ask for full fence, this result is forbidden. No, because this thing is not eliminatable. This is what it says it is. It's the full fencing there. You cannot emulate this with the language constructs.
Actually, I saw this such kind of things in the real code. Sorry, from Aaron that I made a talk about. Probably we don't have to show it to any to the audience because anyone can
it's
say,
unsafe. It's
I can
available. Yeah.
Yeah, but how can you make that fence in the real life?
Without unsafe, you can't. The language rules, follow the language rules. Volatiles or varhandle get volatiles. That's it. You operate in the realm of memory model. This thing is scary low-level stuff, which, by the way, gets us to another interesting example of fences. Look at this result. Sorry, is this the same thing? Yeah. This is usually called Irif, but don't just bear with me for a minute. This is the test. It says, look, there are two variables there, x and y. Right?
Okay.
And we have 4 threads now. Two of the threads are writers. One thread says basically x equals 1. Another thread basically says y equals 1. This guy says R1 X, and this guy says R2 Y. And this guy goes in the other direction, R4 X. The question is, can you see 1, 0, 1, 0?
Yeah, that's a tricky one.
Think about a little bit. What does it mean? It means that these two readers observed the writes to x and y in different orders, right? So this guy seen x but had not seen y, and the other guy, vice versa, seen y, had not seen x.
Yeah. Well, I can, to be honest, I can see what could be what could prevent it. I mean, yeah, we use that OPAQ, but well, so, they not. Yeah, we cannot, of course, rearrange the reads like x and y, but yeah,
So with opaque, we present it to the hardware. So it's really the question to hardware what it does. In x86, which is colloquially known as total store order machine, it does what it says. It provides the total order of all stores of x and y, which means we cannot probably see this outcome, right? Sorry, what? Oh, T, multiple options for T. Yeah, because I here. Right, if you run it on x86-64, it will probably just, it's too low because, well, the downside for exploring this configuration is that if you have lots of threads, you have lots of combinations of compilers, lots of combinations of affinities that you run. So I kind of, let me just pinch it. Don't do split compilations, don't do heavy affinity stuff there. How long would it run? It runs for 10 seconds, and there are no interesting results. I will run with V to get the printout without the interesting results. Right? So this interesting results is not possible because x86-64 provides us with this total store order, right? But suppose we go and do this at PVC64, and of course, JCStress jar is here. What? More recent, yeah. Okay. Really? I don't have. Oh gosh, sorry. Demo gods. Oh yeah, I have set machine here. Why not? And you run it, and there you would see this result, right? So this machine is not. It's not total. It's not provided with total store order for the unsynchronized reads, right?
What is the architecture for this?
This is PPC64, PPC64 little endian. Yeah, but the same thing will reproduce on ARM64, by the way, because what you're dealing with here is that since operations are not synchronized, they can be reordered even if you issue them in the program order to the hardware itself. So let's do the obvious stuff with fences. Let's do the same test, drop these damn varhandles, and just pin all this with fences. You do like the sequential consistent store when you have full fence before the write, and you have the full fence before the write, and you kind of stick the loads with the and the load fences in between them, right? That should work, right?
Well, I would say yes.
Yeah. All right, let's do on the same machine. Set Irif. I know what would happen.
Okay.
Maybe. Or maybe not. Here we go, fences. But when you're dealing with fences, you're basically dealing with hardware because it's then the hardware job to interpret what those barriers really mean. So if you want to maintain the full order of writes and make readers absorb them for PPC64, you have to do this. You have to do full fences before the reads. The load fences themselves are not enough on this particular platform. This is why I wanted you to get the taste of the fences and why they are not exposed to the user. Because to operate them, you actually need to know what you're doing. All right. If I run this test, the interesting case would drop to 0. You have to trust me on that. Or you can get a PPC64 machine and run. All right.
Okay, I'm sorry, let me clarify this one. That full fence and load fence really depends what the hardware think about it.
Yeah, because on PPC64, this thing is a real memory barrier, and this thing is lightweight memory barrier, which does not provide sequential consistency semantics.
All right. Yeah.
If you go, for instance, to, let me do this quickly, C++ mappings, and you go all the way to IBM Power, you would say that if you do load acquire, you can do load and then do the trailing barrier. This is better. If you want to have sequential consistent load, you have to do load, you have to do trailing barrier, and you have to do the leading hardware sync.
Hardware sync, that's the full fence.
Yeah, the full fence. Yes. Yeah, if you want sequential consistency. If you don't want, you can get without it. But acquire release is not about sequential consistency. It does not give you that strong property. Deal with here. Yeah, so fences, not only you cannot emulate them in the language, even if you have access to them, they don't really mean what you think they mean.
Yeah. Got it. Thanks.
All right. A simpler thing, just to untwist our brains a little. Suppose you have this interesting result. So interesting test. You have a volatile X. We already established that volatile increments are not atomic, right?
Yeah.
But the more interesting question is, if you have the test, each of those threads increment volatile 5 times, how many updates can you actually lose?
Up to 5, I think.
Up to 5, right? So you would say that if I do the, this is, by the way, arbiter in JCStress, it's the thing that's run after all threads finish. So it's kind of observing the final state there, right? Mm-hmm. So you say that if I read R1, I would read what, 5, 6, 7, 8, 10, right?
Yes, as soon as it's volatile, well, I would expect it this way.
All right. Let's run it. This is a fun example because it's so obvious when you know what would happen.
Well, I can expect that I'm wrong, but at least my current knowledge says me that.
Yeah. So what about these cases? Yeah, you're right. This is kind of obvious, right? You think as if this is a volatile thing. So the worst thing that might happen is that I read the previous value and I collide with the thread that also did the previous value. So I lose this one update there.
Yeah,
so
but it's volatile. So
yeah, it's volatile, but I still have these two things. And this is an interesting thing. If you think about it, you can see the timeline like this. Explain it. Right? You have one thread reading 0, then getting stalled. Other thread does these updates. Then first thread unparks, unstalls, stores 1. And the other thread does the final operation, reads 1, gets stalled. This guy does its updates, and yeah.
Yeah, now I see.
What this example shows you is that if you have badly synchronized counter, you can lose the unbounded number of samples. Right? Right. Mm-hmm. We probably would skim over this. One of the things about array volatility, I think there was a question about array finality, but it's a similar, I think, to volatility here. Suppose I have this array. It's volatile, by the way. Do note that. It's only 2 elements, and we store like in 0 in the first element once, and we read them here. It's pretty much like X and Y case, right? But with array elements. Yeah. So the question is, can I see this? So can I CP1? Yeah, expect kind of jinx it, but yeah.
Okay, no. But I think yes, because yes, the reference on the array is volatile, but the values are not. So that's why we have that varhandle arrays in the latest JDK version.
One of the ways to think about it is that this store, it's stored, but it's not a releasing store, right? It's not a store to volatile variable. It's a store to the non-volatile element array. And even though the array is declared itself volatile, the elements are not. So if you run it, let's do. And yes, you're right. If you want to do the volatility for elements, what do you do then? You go and do varhandles. You say, I do this special type of varhandle, which then says that I can store, this basically says A11 as volatile. And this says R1, A1 as volatile. Right? So in this case, 1 and 0 is not allowed anymore. And we can clearly see that in the declaration side volatility, when you have the volatile on the array field itself, you have this test case. And here lurks this varhandle case, which has no interesting cases at all because it's now forbidden. Right? Okay. So great promise of the varhandles that it not only gives you the relaxed modes, but it also gives you the volatility in the places where it's not achievable by other means. right. All right. Oh, this is not this. Surprisingly, many things about proper placement of acquire in releases are understood on the simple examples, but then you cannot apply this to the real code. The usual trouble that I see is this. Suppose you have a list, array list. It's volatile. You have this list here. You initialize it, and you release it right away. Yeah, it says prematurely released because it's prematurely released. And then you add something to this list. And in the reader, you say, look, I read the list in the local variable. If it's empty, I will reply 0, will store 0 into my result. If it's not, I will get the first element and see what's in there, right? There's 42, so I would just unpack 42 from there. Or if it's null, I will do -2. Or if I happen to have array out of bounds exception because this guy can throw it by spec, that I will do -3, right? Otherwise, if I don't see list at all, which is possible if this actor runs before actor 1, I will do -1. So what cases do you think are possible?
Well, I definitely think that 40 we might not see 42 in the list. Well, because once again we didn't have any store after we acquire. So I think our array index out of bound exception is really possible.
Possible? Why? We have just checked that's not empty, and we are doing the lowest possible index here.
Yeah, but so we. Yeah, because of the consistency state, because we empty. And I do believe in the array list there is a counter of the number of elements, right?
Well, yes, there's size, yeah. And
size.
this guy, if you go there, array list, it says is empty, is basically size 0.
Yeah, so it might be that we update size, but we didn't update the value itself. So.
Right. Have updated size, but not updated value itself. So if we have, okay, all right. So if size is updated, right, but the value is not there, this guy returns true. False, right? It's not empty, right?
Yeah, but vice versa. Yeah, so we kind of we updated size, but we kind of recall the previous value because it's not any store, but
no, it's really confusing. I understand this.
Yeah. So, but the main idea that array list is really for single threaded, and if you want to use it in the single threaded, so this is obviously a race condition. So I would expect any outcome.
Yeah, but let's agree that this is possible, right?
Yeah, this one yeah, for sure.
This one is also possible. It's replies 42, right? This one is also possible, right?
If it's not, yeah, sure.
Why?
Because size is not empty, and
yeah, it's not empty. We get the 0th element, and it's null. What the hell?
And it's null. Yeah, you're right, and it's integer. Yeah, because the reference on the actual value, because it's bound, so now it's not an int, it's a reference on integer. So it might be possible that so we didn't have any fence between that add and this read. So I would expect that. So as you told before in probably very first example, so we can see a null value.
All right, let me start running it in the background, and we will dive a little bit into the how array list works. So let's go and see what add does. Array list. What does it say? It says add e to this element data. This is probably from the superclass. It adds something to the array, and then it increments its size.
Then increment size. Well, but still rearrange is possible. So we can expect it in any direction.
So what are the results here? So -3 is the array index of the bounds exception. Right? So we have figured that this size is not empty here, size is not 0 here. But then when we get here, read the size again, realize that it's now 0, and we threw out of memory out of bounds exception because we're trying to read out of the thing there. But listen, I told you that the size is the same field, so coherence is probably on our side there, right? There is a single total order modification order to this single variable, right?
So it's not volatile. It's like your first example when we have double read R1 equal A, R2 equal A. So it's the same thing.
Yeah, it's the same thing. Even though we are running on x86-64, which is total store order. We store the element to the array. We updated the size. We read the size here once and here the size there once. And we have basically a coherence violation here, which manifests in the complicated code, right? Because what says here, size 1 basically replied, and here size 0. Oops. Yeah. But yes, it's one of the outcomes from this test. But also notice that you put volatile on the list, and you basically misplaced it because when you do this, you still do unsynchronized collection access, which exposes you to nulls, which exposes you to array index out of bounds exceptions, etc. So volatile means nothing here. If you really want to do this, you have to do this way. You have to say list L add list L. Here you do everything locally. You construct the thing locally. You do release because list is volatile. This guy is acquired.
Yeah, now it should be safe.
Yeah, now this is impossible, this is impossible, and this is impossible. Right?
Hang on, but if it's not, it's possible that we see the 42.
Oh, yes, sorry, yes.
Not now, yeah.
Yeah, all the exceptional cases, the negative ones, and this one is not possible anymore. We see the full contents because we had properly
safe publication, right?
Safe publication. We safely publicized this list. Yeah, exactly. All right. Synchronized or not fences, we have covered this already. And one completely brain damaged case.
I'm ready.
Suppose, just bear with me for a minute here. Suppose you have this holder here, class, which carries the volatile field X. And you initialize it in constructor 42. And you have this holder field, and you publish this holder racely, right? And then you read it into local variable, null check it, and read X from there. What results do you think are possible?
Oh, so, not equal null.
Let's count the exceptional cases first. Can you see this?
I think yes, because this means we run it first before the third one.
Okay, so we are here. We basically ask ourselves whether we can see 42. Can we see 42 here?
Yeah, definitely 42. Well, I'm thinking about 0. Yeah, I'm thinking about 0 though. that the holder itself is not volatile. So
but this thing is volatile.
Yeah, but
and this is a volatile store. And this is a volatile read. Don't you know that volatiles provide promptness? If it's volatile, it's probably the latest value that's
well,
stored.
well, from one of your previous talks, so you recommended to make the happens before edges. So I'm under the impression that we're missing some edge somewhere.
Yeah. So let's run it. We're running out of time, so let's run it. Correct. What? Again, wrong Java. Sorry. Maybe I should even. x86-64, probably not that interesting. Total store order, everything is fine there. Yep, no interesting results. Now let's do this at R64. We have here 17.
I have a hint from Vladimir Sintikov. He said that safe publication age is missing. So that's
there's no. It's not safe construction. Yeah, it's not safe construction. Here you go. This 0, even though that field is volatile, and it only manifests, as far as I know, on ARM64 and sometimes on PXE64. And the reason for that is this is still a race. It doesn't matter that this thing is volatile. Volatile is it's completely irrelevant that this thing is volatile. It's in the wrong place. No memory ordering for volatile will help you to resolve the race that happens elsewhere. It's not even it could not even be construed as the release because it happens before. Well, it happened in the program. It is before the store of X here, of H here. So
yeah, but we can easily fix it if it would be a final, right? So like from one of your papers. So volatile is not
right.
That's your volatile offer.
Yes, but this is synthetic case. But what about the real life? This is atomic integer. Atomic integer has the volatile int value. It cannot have final int value because it's mutable, right? So what would you say? Can I get 0 here?
Well, I believe in Doug Lee, so that's no.
But it's the same thing. It's the same holder with the volatile int x, and it's basically the same example. You have recently published the atomic integer. There's a 42 that's stored in the internal volatile int field.
Could you show?
So I'm very sorry, but unfortunately we add all the time slots, so that's I need more time and not absolutely. Okay.
Yeah, I will just leave you with this, so that you will be.
I'm very sorry. I just want to remind that we can continue the talk in the discussion zone. We especially ask our support team to start the record. I think there's a good idea to start a record with to finalize the workshop, and after that switch off the records and to go to off-record discussion zone. So sounds good?
Yep.
Okay, everybody.
I like this space. This is the final. Yeah, this is the
okay.
Good space
Everybody is welcome to the discussion zone right now. Press the Zoom button just under the web player and follow Aleksey and Ivan in the discussion zone. And stay tuned. We are going to closing of the day number 3. Thank you very much, Aleksey and Ivan.
All right, a taste of real bugs. This is in JCStress speak one of the bugs that was found by JCStress. So again, the same damn thing all over again. X and Y. Y is volatile, so it's kind of volatile guard for X, right? So do you think the 0-1 case is possible?
Shouldn't be because of
It shouldn't be because it's written so on the slide. It's illegal under JVM.
Okay. So yeah, because of the happens before rule.
Yes, because it's volatile. It's a release. Store to Y is the releasing store. Read from Y is the acquiring store. Everything you find there, but it breaks if you put this statement there. If you uncomment this, I could not show you in the real code because this bug was fixed, and this is a C1 bug. C1 bug basically says there is the common sub-expression elimination pass, which basically tries to coalesce the similar sub-expressions to their form, and it notices that, look, here's the store of x to temporary t, and here is the x, by the way, as well. So it transforms it to this thing. It's a bug because in doing so, you should have tested if there is a synchronization operation between these two guys. If there is a volatile read, you cannot do this kind of coalescing anymore, right? You have to do this test. Yeah. So that's a simple bug in
When was it fixed?
Let's see.
Sorry, by simple you mean it is simple to fix, or was it simple to find?
It's simple. It's actually both. It was the very first bug that was found by JCStress back in 2012.
Okay. So more or less modern version should be.
I mean, on the other hand, it took like 7 years since introduction of JVM.
Yes.
So simple is a stretch.
That's what scared me the most when I was basically developing JCStress in anger because I realized suddenly that the basic guarantees of the language are not verified. Like, okay, 3 billion devices run Java. All right.
3 billion devices on fire.
Another case, immortal reference. This thing I think was found by Heinz Kabutz, and this was the inspiration why JCStress got its so-called termination tests. Termination tests are basically checking whether the test terminates. And here we have this weak reference, which is pointing to some object obj. And one of the threads is just waiting busily on that reference to become null. When that reference clears, its reference is null, and the actor first exits. So what actor 2 does, it doesn't wait for GC. It just goes and sets clear, set reference to null. Expected that the thread terminates, actual behavior thread is stuck. Why? Well, if you look at the reference, if you look at the get, you will realize that there is the non-volatile field referent, which is set by GC. But from the Java perspective, it's a non-volatile field, which means you can transform this busy loop over a non-volatile variable into checking once and then just reducing to while true. Whoops. And you never exit from here, no matter what happens. Yeah, and it was also fixed by recognizing that this operation here is really special. It's not even compiled like that in the hotspot. There is the entire bunch of barrier set code written specifically to support reference get. Mostly because you don't only have the memory effects here, but you also have interaction with GC because you might resurrect this reference and you have to notify GC about this. But by doing so, you can also do a proper memory semantics there, so this kind of transformation is not possible. Yeah, that's fun. Another fun test also found by one of the Heinz's students. Everybody does this, right? You wait for thread interrupt. You probably do something useful in that while loop, but you otherwise wait for thread is interrupted, and you wait for some other thread to interrupt. And expected that the first actor will terminate. but it doesn't. And why? Why, you say? Oh, sorry, this test terminates, but this test doesn't. If you just hoist this into this separate method, it doesn't.
Because some sort of intrinsic.
Well, I mean, thread interrupted actually used to check the flag in the native. The definition for thread is interrupted was native method. It was an intrinsic. It was specifically, the access to this field was specifically inlined by the compilers. But in doing so, in that IR, it was not declared any source of volatile there. So as far as the rest of the compiler is concerned, it's just a plain field read, and you get all the same behavior as in the thread before, in the case before, right? You have the busy loop on the non-volatile variable reduced to while true, you're stuck.
Yeah. Yeah, that's actually why I hate that thread interrupted method at all, and try to avoid and use just some flag, which we modify in interrupted event.
Yeah. Yeah, since then it got better because the interface was reworked and now it's just plain volatile field. So it's not that problematic anymore. But even back then, in the JDK 8 timeframe, it was fixed by actually writing this intrinsic correctly. Right. Oh, yeah, this is my favorite one. This is also one of the tests that basically answered my question whether you want to do combinatorial tests in JCStress or not. So we've talked about access atomicity, right? That you want to have indivisible reads and writes for the built-in types. We know that longs and doubles are exceptions from this rule. Shorts are not exceptions from this rule, right? So if you have this, you have S, which is default initialized to 0, and you have it's initialized to all bits. You kind of want to see either zeros or Fs, right? And that's indeed the case. That's certainly done by JVM. Well, it's required by JVM and it's done by implementations. But what about this? What about if you read it in a temporary variable and then kind of try to store each byte itself? At that point, you will suddenly realize in the buggy VM that you have like these torn values there, which makes no sense because I told you that JVM defines behavior under the races. If you read from the memory once, that's what you read. You don't get to do 2 reads all of a sudden here, right? So you would think that when I read S, I read it atomically, so I read either all zeros or all Fs, but suddenly it isn't. And the trouble is with compilers, if you follow how compilers compiles this code, it says, look, this load is actually a short load of SX. And those two things, if you rewrite this in IR, it will be like this, right? You shift T, then you end it with mask, then you store it to byte. Then you try to simplify this graph. First, you recognize that this shift by 0 is identity by T. Then you realize that loading, basically ending short T with FF gives you the lowest bits of T. So at that sense, you can just byte store the T itself because the store will handle the truncation, right? Is that understood and understandable, Ivan?
Yeah, at least for me. Yeah, the
Yeah.
byte store.
Well.
Sorry?
For me as well.
Okay. All right, but let's go to the other statement. It says, look, the same kind of thing, right? We shift by 8, and yes, it's not in the entity, but since we're ending it with FF, we kind of cut the lowest bits as well. And since we do the store after that, we can just ignore this end, right? This is also understandable, right?
Hang on. So we shift and we don't need.
Yeah. Yeah, so end selects lowest bits and byte store already selects those same bits. This is a plausible simplification. And then you say, hey, look, since we don't care about the sideness of this thing, of this T, we might as well convert it to the unsigned short load of S for the reason, for the cost model reasons, because it's cheaper to do for some reason. And we inline the remaining T to the other thing. In doing this simplification, we introduce the load of the original SX, which is
which is bad.
Yeah,
which is bad.
That's really mean.
Yeah, that's really mean. Yeah, it's not. It's against JVM. Yeah. So this thing basically compiles to this. You have like a zero store. You have zero extended store, and signed extended store, and that's kind of bad. So this is a plain compiler failure. It goes against the spec. Spec explicitly disallows this. It's bug. It's fixed. Another thing, volatiles. I love volatiles. Suppose we have this volatile double D. Yeah, we know that it's atomic when we have it volatile. So if we store all ones and then read from there, we can expect either all zeros or all bits set, right?
Or one. Yes.
Yep, it's excess atomic at this point, right? It's good. The actual results is that plus garbage on bad VMs. Okay, you start digging, and you realize that this thing, by the way, only reproduces in the interpreted mode, not in compiled mode, only in the interpreted mode. This is why if you want to test concurrency, you test in the multiple VM modes. If you go and look at the native parts of the unsafe that handle like native code of this, unsafe get double volatile is defined like this macro, which does ordered access load acquire from the computed offset of the field there. And normally you would think it would compile to this. Even on 32-bit VM, there x86-32, there is the FPU, which you can use to read and write 64-bit values atomically. And this is what it does. It has float load from the address here and store to the address here through the internal state of the FPU. And these two guys are 64-bit atomic. This is what we want for the double, right? These things are actually hiding in this ordered access load acquire, which is these carefully written for the specific platform in the native code, right? But what it actually compiles to, because of this thing is volatile type name, for some damn reason, the compiler says, look, since it's volatile, we really want to read this into our local variable first, doing two distinct reads and writes. And then after that happens, we'll certainly do this load acquire dense with the 64-bit atomics there. But it is too late at this point because you already had non-atomic reads in the first 4 instructions. Right? That's an interesting thing, but this thing is volatile. It's the volatile from the CLAN, and this actually broke your code. Is that understandable?
Could you repeat that the last part? This is volatile from C code.
Yes, yeah, because this guy is CPP file, right? It's basically macro defined in the CPP file. Yeah, this volatile is not Java volatile; it's the volatile from C++.
C++.
Yeah, so it basically says that treat it as the external something, and compiler actually treats it. It says volatile. We will read it in place here, and then of course, we will do load acquire stuff there. Okay, that's bad. Yeah. Yeah, in other words, volatile syntaxis does not guarantee atomicity. Yes, but what this example says that it not only doesn't guarantee atomicity, it's also actively hostile in the examples like this.
Just a small question. What is the meaning of volatile in C++ in short? I mean that they didn't introduce a volatile if they don't use it.
It mostly has to do with the interfacing with external memory. It does not have to do anything with memory consistency.
Okay.
Think about if you want to map something on the memory map register, the hardware, and you don't want optimizer to do anything with it. You say that if I write into the volatile, please do write into memory at that address. Yeah.
Ah, okay. Okay. So this avoids using registers.
Yeah, pretty much. Yes, it says it is a memory. Go and read memory. All right. Next example is Decker. Again, lots of things comes from the simplest example. We already established that the result 0, 0 is impossible, right, in Decker, because if access to x and y are threshold consistent, either of two last statements are the last, so they have to read, at least one of them has to read 1, right? But if you run it on power, in the early powers, it's not the case. And the reason for that is twofold. First of all, when you write the backend for the power has lots of registers. So you want to use those registers. How do you use it? You want to do the reads as early as possible and just carry the pre-read data throughout your program unless something prevents it. And the second piece is that there are optimizations in the compilers which coalesce or remove the barriers. And in one of these optimizations, there's a bug. What's a bug? Which says that if I do this X and Y volatiles, I basically emit memory barrier of one kind, store memory barrier of other kind, load memory barrier. It basically removes this memory barrier between the load and store, thinking something else. You get this kind of graph. And at that point, the power-specific optimization kicks in and says, hey, look, this load can be scheduled before the store because it's profitable to do so, and you break. Yeah, and that, by the way, highlights the necessity of testing on many platforms, because some platforms might surprise you with interesting, still compliant, but interesting examples, or non-compliant bugs. All right. And the other thing, fairly recent, there is such thing as JVM in OpenJDK. This is the C++ interpreter, which is very good for portability because you carry hardly any platform-specific code there. So again, the same thing. Y guards the value of x. You don't get to see 0, 1. And you really don't unless you run on R64.0 with y being long, either long or double. If y is int, this doesn't happen. It only happens with long and double is there. All right. And the problem is in this piece of code. Can you read it, Ivan?
To be honest, I give up.
Yeah, it's even more horrible. It's more horrible in the actual code, by the way. It's a barrier selection thing. It's basically selects what to emit when the native code requests a barrier, and it's 0 specific stuff. And of course, this thing is platform specific, right? So we have a case for ARM. If it's ARM, you do the kernel data memory barrier. If it's not ARM, then it's PPC, and you do always sync, which is lightweight sync. We talked about before. If it's not, if it's alpha, you do sync synchronize,
If it's not alpha, you do awesome volatile memory, which is not really, which is the compiler barrier, not the hardware barrier. Now, answer which path Arch64 takes.
ARM. ARM.
No, oh,
The
sorry,
probably
sorry,
first one.
In hotspot nomenclature, ARM and Arch64 are different things. This is ARM32.
Okay, probably the first one. Yeah.
No, but this is not ARM. This is Arch64. It's a different thing. So
then none.
Yeah, then none, and you basically have no memory barrier there. Whoops. Yeah, so we basically rewrote this to be more defensive, and this is, by the way, a good rule, is that you always default to the strongest thing ever. So we actually defaulted to synchronize, and then we provided platform-specific exceptions when that synchronize is not needed on the barriers, and that kind of solved this.
And Aleksey, just one question. I thought that most PCs we are usually using, except for the ARM processors and other devices, they are all 64-bit processors, aren't they? So that even if you just have a byte, the computer will not have a byte in the CPU because all registers are 64 bytes. But it looks to me a bit that the other architectures are not so far, that they are kind of 32-bit processors and things like that. And doesn't that matter somehow? That it depends on how large the registers are in the end?
No.
You know what I mean?
Yeah, I know what you mean. Not here, and not pretty much anywhere else. Because you are allowed to use parts of the register to store your data. That's fine.
Okay.
Yeah, would Elif would be much more readable here. Oh, you should look at the actual code. It's just, oh God. No, I actually rewrote with Elif, I think. Let me see. Oh, yes, I did. Of course I did. Yeah, so it defaults to strongest barriers, and then it has else Elif defined x86, Elif defined PPC, Elif defined ARM. Right? Fun bugs. And speaking of zero, ARM32 was also broken on this, and it's broken so much that JCStress did not even start, which is kind of a weird half point to JCStress for this. And it doesn't start with a weird exception. It says, look, I cannot allocate direct buffer memory. I already allocated 0, and the limit is negative value. Like, what? Yeah, and it happens somewhere early in like locale initializations or something like this. And if you look closely and you just nail this, you realize that volatile longs are broken. And you go to this code, which basically, this is the atomic copy 64, which is the helper method, which is invoked by 0 when it wants to access 64-bit type atomically, like long, volatile long, or volatile double. And this is what it does. In ARM64 assembly, there is the atomic load of this value to temporary variable. Here it is. This TMP is the reference to the local variable here. And then it stores this long here with this C statement. So this part works. We are loading it atomically, no doi. But trying to do this kind of thing in C, it's not atomic anymore. Yeah, and you introduce basically problems here. So the fix is basically to do both atomic read here and both atomic store to DST in the same kind of inline assembly stuff there. All right. That's it. Do you have any questions?
Guys, help me out.
I have just one question, but it might sound a bit ridiculous, but I sometimes wonder where you know all that from, and because some things, they are not in the Java language specification or somewhere else, and I sometimes wonder whether you are looking into the C code or C++ code of Oracle or whatever to see how things are working, because So what is your let's call it your richest source for knowledge? It can't be books to me.
With the rare exceptions, most of the issues that I deal with are implementation issues. So yes, Hotspot code mostly. And the thing is, compared to other places in Hotspot, handling synchronization is one of the well-written parts of Hotspot. Probably because after discovering bug after bug after bug, it was gradually rewritten and rewritten. And you kind of can, yeah, it's not that complicated, I guess, if you are already savvy in the Hotspot code. Yeah.
Okay, because I mean, in the tools that you created, Java object layout, Java memory, micro benchmark harness, and JCStress, there's a lot of knowledge behind that. I guess I wouldn't be able, or others, to write that down, because I would wonder where I would get all the information for that.
Yeah, but it's not like you have it as the I don't know, prepackaged stuff. You learn it as you go. You just, well, like for split compilation thingy, I didn't know it was possible. I asked myself if it is possible to compile different methods with different compilers by asking from outside. I basically grabbed around in the Hotspot code and I realized there is a facility within the Hotspot which allows me to do that. And I realized there's a job for it which describes the external semantics for that code. And I like it. That's what I need. That was my problem statement. This is the steps that I did to get there. And I realized there is something that's useful for it. It's not like something that comes to you in your dreams. You just churn through implementation, docs, etc.
Okay, thanks. It's really amazing what you know.
Oh,
yeah. I have a question about the deferred job to improve JVM, and so do you think the question number one, will they continue the work under that job, and the second one, will be included the the lambda semantic for capture the value outside world, well,
the answer is I don't know. The problem with this kind of jobs, but and with the jobs in particular, is that you have way too few boots on the ground to actually make it happen. So you have like, I wouldn't say you have to have the specialized knowledge to do this kind of stuff, although you probably should a little bit. But more often you just need just sheer and the availability of time to actually work through all that crap. And it's rarely to see that, picked up by community, for instance. It's usually a paid job that you could do stuff, like this. And those resource pool is limited. So,
well, if I may comment, if we're talking about revision of JVM specification, but actually is a current scientific problem which isn't solved to the diocese, and probably Java community waiting when the C++ specification will be finally finished and will copy more or less with adaptation to the Java specifics, because we have a lot of discovery corner issues involve problem memory and models.
Yes. Everyone kind of, and it's not Java specific, it's C and C++ specific as well. Everyone tries to find the next good formalism that is easy to understand and it provides good results and it's simple to implement, etc. Because I mean, everyone I think who is involved in memory models realizes that both Java and C and C++ memory models, as stated, are extremely hard to deal with. Even for the people who kind of do it on daily basis. I don't know. I could probably tell that I was I felt confident about my JVM proofs after about 5 years of doing them. It's just they are way too formalism is way too counterintuitive and quirky to work with. So yes, everyone looks for the next big thing. Meanwhile, we kind of carried by the libraries and more or less like hand-wavy reasoning about this. This is why varhandles are good, because they provide you kind of with the high-level behaviors without boggling with the intricate connection to the spec. S3 atomics in C and C++ kind of also give you practical examples of how you deal with this. Yeah, it's heavy. It's very research-rich topic for which you do not have a good and compelling answer as of yet. I've seen many proposals that look more or less good, but the thing is, the JVM proposal as adopted right now also looked very good back then. So kind of cautious.
I see. Could you take a look on the chats? I've sent you the question that I've already asked you some time ago. Can we make a test for this guy with JCStress to prove that definitely there is no data race?
Well, we can't prove anything definitely. We can prove that it's broken, but we cannot prove that it works. But let's see. What is this? This is completable future, right?
Yeah.
Did I have the completable future test here?
Oh, we do.
Completable future completable. Oh, I have it in Scratch. Really? Okay, fine. We'll make it that one. Completable. All right. How do we call it? What's this? Let's say then apply. Then apply. Okay, let me just copy paste it. So we need actor. Void actor one. First actor does what? It does initialization, right? My 24. This guy makes. Yeah, so this feature it should be a field, right? No, wait. Wait apply, it returns something, right? It also returns completable feature. So we need to save this one. Yeah. Like this, right? And the other actor says CF, what's the get or apply? Get, right? And we want to maybe unpack it as null, right? Or this guy returns integer. Does it throw exceptions? Yes, it does. Li. If li equals null, does not equal null, then RR1 is li unboxed, right? It is -1, right? Okay, now we decorate all this stuff. First of all, this is JCStress test. Second of all, it carries the state. And third, it comes with outcomes. Outcome -1 is plausible, right? Boring. This is boring. 42 is also acceptable and also boring. By the way, we can do like this.
No,
All right.
42. No, 42 is not acceptable, right? Because at 42, that means my.
Oh,
is
sorry.
actually,
Sorry.
Oh,
Yeah. Okay. So it's forbidden.
yeah, forbidden.
Bad. So what we actually want is 42 plus 1 to 3, right?
1 to 3, yeah. Well, we can change
So
the
it's
number.
1765, right? Is that right?
Yeah. Yes.
Yeah.
Yes.
Okay. Is that it? And by default, every other outcome is forbidden. So we could basically remove this, only list acceptable cases. All right. Let me just install Java here.
Does it cover null pointer exception cases?
Yes, here.
I mean, cf.get.
Oh, CF. Oh, God. Yeah. Yeah, sorry. Let's see. Yeah, if LC not equals null. Goddamn nulls. -2. Let's say it -2. Okay, test custom. That's it. Shouldn't do clean install, but yeah. Oh, other exceptions. Really? I cannot. I can do this in JMH. I cannot do it here. Sorry, I should really fix that in JCStress. Catch this here. This sketch blocks. This would not happen, so we don't have to put it into the outcome. But did it auto injector failed? What? Yeah, sorry, because I changed my Java version mid-flight, so my other dependent artifact was compiled with newer version of Java. Always do all the dependencies. Yeah, that guy, by the way, was about to inject intended to our field here. All right, -t. So how did we call it? The apply test. Yeah. What? JCStress samples. We need test from in the other module. Okay. Nope, no other results. Okay. We can do this. We can go to other platforms and see what's going on there. Then apply. So this is ARM64, and this is PPC64. Whoop, possibly out of memory. Ooh, this is a nice failure mode. So this guy started this threads.
Too many completable futures.
Yeah, too many completable futures. Damn, and R64 is good. So maybe it's a limit problem. How many processes can I run? Yes. Yeah, so Arch 64 completed fine, right?
We're good.
We're
Awesome.
almost good.
So
Almost.
we can use completable future without no fair, with no fair.
Yeah. I should say this more actually. At least it's not horribly broken.
Yeah.
But you really want to reason with the spec whether that result is plausible or not. And I think we discussed this, that it is. So in here, you have the capturing in this lambda is good.
Something like final field to the constructor and
yeah, because it's basically the private final my, which is implicitly assigned here. Yeah, and your final
We
semantic.
forgot an int.
Yeah. But this is just a sample. It's not illegal Java anyway.
Okay.
So I think. Oh yes, it is illegal Java. Yeah. So it's basically like this, right? It's the same thing.
yeah, and probably with the constructor, right?
Here's the init. It's the same capture here.
Okay, yeah. Final field can be initialized only in the constructor. Correct. Yeah, thanks. At least now I feel a bit more safe.
All right. Any more questions?
Yeah, and what about that atomic int? So, but at the moment we have to mark volatile every atomic int, right? Or final at least.
No, I don't think so. I think you just wait for the VM fix for this.
Well, but I don't know if we use Java 11.
Yeah, then wait for the VM backport. Yeah, because I think it's universally understood as the bad thing. Yeah, otherwise, sure, do not publish objects racely, even if those objects are from Java to concurrent.
Okay.
Aleksey, you showed a couple of examples and errors when some long fields were not atomically handled.
Yeah.
But did you came to the things when the near locating short was handled both because some wide memory access operations was applied wrongly?
Oh, I never seen this happen in the VMs. You can construct this test case. For example, let me, I removed some of the tests here so they don't distract me. But if you go to samples, where am I? Samples, JVM, basic, word tiering cases. You can, first of all, you can construct it yourself like this with bit sets, right? You can destroy one update because bit set kind of stores bits per int there. And one of the interesting cases is varhandles again, because there is no atomic Boolean field updater, because even in the atomic Boolean, the value is integer. But if you have the Boolean field, you can acquire the varhandle over that field like this. And then you would like, you can do cases on that field, even though technically you might have a platform which cannot do a single byte case, like ARM 32, sorry. So on R64, R64 is fine, x86-64 is fine, every x86 is fine. ARM32 is not fine because classes there are 32-bit long, at least. So you do weird stuff like, I don't know if I can decompile this. Save. Yeah, let me go. What I'm looking for, this guy. Compare. Yeah, you basically simulate that bite-sized compare and exchange by doing the full word classes here. Right, you determine the word offset, you determine the shift within this word, and you do the whole cast there. And that way, even though you do wider access for the narrower type, you still don't have word tiering because you kind of agree on the integer word that you are working on. So you don't lose any updates. Both classes would succeed in this case. That's what test fails, tests that both classes succeed, even though they are underlying, behind the scenes, they are contending over the same integer word. Yeah, this kind of things. Word tiering is prohibited in Java. So this is the length that you should go to actually maintain that property. That answer your question.
Yeah, I just thought maybe you somewhere solve a bug related to this.
No, it's usually very hard to construct, I think. I mean, if you have a single, let me remember. Except for the inits, compilers do not usually call as different stores. Yeah, at least not hotspots compilers. So it's hard to come by.
Aleksey, you did mention that you use different compilation modes, like different compilers for different methods. And I wonder if you do change compilers dynamically.
Which compilers?
I mean, C2 and C1 or different compilation levels for Nectar during the runtime. Or if you are
during the runtime, no. During the runtime, no. It's only the forked VM configuration.
Okay, I see. So it's like pull request welcome.
Yeah. It's basically, yes. It's basically, if you want to, it used to have the optimization support within the VM, forked VM, but it's tedious to support and without a good reason. If you can fork another VM, it's easier to just configure it from outside.
Well, there is probably a source of issues like methods de-optimizing and switching between different methods. So it might be a source of bugs. Or like OSR compilation.
Yeah. It tests implicitly with the default configs. At some point, you have to kind of cut your losses, right? If you test every single configuration you can think of, you will never complete your testing.
Yeah, that's true.
Yeah,
I wonder if you use like Whitebox API. Is it worth using?
I used to use it for the online de-optimization support, yes. I ditched it because I realized that it's easier to do this from outside. Probably if I do the optimization, I would just go and start the VM with XX plus de-optimize a lot, and that would give me the same effect. Right?
Yeah, well, I actually not a question, but I just want to say that it was just a cool, very cool presentation. I'm just very impressed. Like thank you. Yeah, sure. No, not a question actually. Just no.
Yeah, well, to be honest, I would like to join. So that was fantastic. Thank you, Aleksey, for this journey through JCStress.
Yeah. The parting thought is that I covered like a fourth of the JCStress samples. So if you want to know more, just go and try and run it and read the comments there. That will probably take you a day or two, but it would be fun.
Or your entire life, like in your case.
Yeah. All right,
Well,
that's it then, right?
Yeah, I hope I passed my JVM exam. at least C level. I don't know.
Yeah, you pass it when you die. Yeah.
Okay, thanks, guys. If you don't have any question, we can wrap up. Thanks once again, Aleksey.
Thanks again for Aleksey very much.
Yeah.
Thank you.
Interesting.
Very useful and very interesting.
Yeah. Thank you. Ta-ta.
Bye-bye.